Hi, everyone. Welcome to the Water Research Foundation webcast on Project 5120, Utility Field Guide for Developing a Cyanobacteria and Cyanotoxin Monitoring Program. We're very excited to have you be joining us today. My name is Sydney Samples. I'm a research manager at the Water Research Foundation, and I will be moderating today's webcast. We have 4 fantastic speakers lined up today. So we'll start by hearing from Dr. Eric Rosenfeld. He is the Vice President and Drinking Water Practice Lead at Hazen and Sawyer. We're then going to hear from Mena Elnahas, a PhD candidate in environmental engineering at the University of Toronto. She'll pass it to Dr. Sushira Pohuraju, a principal engineer at Hazen and Sawyer. We'll go next to Dr. Hussein Almutaram, a senior research associate at the University of Toronto. We'll pass it back to Dr. Eric Rosenfeld to finish it, and then we'll have a moderated Q&A with everyone. So before we get to that, we have a bit of housekeeping to go over. So throughout the session, you can type your questions in the box below the presentation on your screen. We'll answer as many questions as possible, but if we don't get to your question today, we'll make sure we follow up with you afterwards. So if you've got a great question, make sure you ask it and put it in the chat. You'll get an answer one way or another. Next, the slides and a recording of the webcast will be available on our main website. You can download the slides now, as well as access a link to this project's page under Event Resources on the bottom left of your screen. The final report and the Utility Field Guide have already been published, so we encourage you to check them out after today's presentation. A certificate of completion will be automatically generated after the webcast. Any questions related to this certificate should go to Michelle Suazo. Lastly, we will have a quick survey at the end of today's webcast, so please stick with us through the end to provide us your feedback so that we can make sure these webcasts meet all of your needs. So with that, I would like to pass the baton to Dr. Rosenfeld to kick us off.
Thank you, Sydney. We're really excited today to talk about the project 5120, which was the Utility Field Guide for Developing a Cyanobacteria and Cyanotoxin Monitoring Program. We had a great team assembled for this research, and it's really nice to have the opportunity to talk through some of the findings and to present some of the materials developed in this project, which turned out great. The crux of the driver behind this project is the recognition that I think everyone who's here today realizes that harmful algal blooms are becoming more frequent and more intense. Sydney mentioned as we were putting this together that this might be the perfect time of year to put together this project because there really is need for streamlined guidance for utility around developing monitoring tools for both cyanobacteria and toxins associated with those cyanobacteria. And we took the project to develop a risk assessment tool and also some tools for interpreting the data that comes out of these monitoring tools. And really the impetus for this project was to build this guidance to sit within the broader group of cyanotoxin resources developed by the Water Research Foundation, which is a great set of resources, quite extensive. And there's just lots of materials out there for dealing with harmful algal blooms. And then the last piece to mention is that this project 5120 was really built upon previous work from the Water Research Foundation, including Project 4692, 4912, and 4914, amongst other projects that were already out there. So the research objectives and tasks for this project were to develop this risk assessment framework for utilities to use, considering source water, toxin release, and the risk associated with insufficient toxin or algal cell treatment within a facility. It was to compile and synthesize available information together and create some what we call method cards, and we'll talk and show some of those later, but they're designed to be simple to use summaries of the methods, and to pull that together to develop guidance for data interpretation, especially focusing on resolution of discordances. So if data doesn't match between methods, or considering things like interferences associated with methods. And then we pulled that together into a utility field guide to to help utilities develop a risk-based monitoring program and design an opportunity to design a way to get ahead of some of these events. The architecture is designed as such. The first step, as we mentioned earlier, we took results from previous projects, including 4912 and 4914, which presented guidance on decision trees and developing programs and took utility guidance. And then we took that together with and developed this project, which is here in the middle. And there's some specific components of that project, including risk assessment and foresight, guidance methods for selection of the right methods, how to implement the methods in a monitoring design development, and guidance on executing and analyzing the data. And as we mentioned before, this is really designed to sit within other materials developed by the Water Research Foundation, particularly related to 4692, which talks about treatment of intra and extracellular toxins. The project tasks associated with this project, the University of Toronto led the risk analysis task. Hazen led the compilation of the monitoring parameters. University of Toronto developed the materials for analyzing and interpreting data, and then Hazen took the lead on developing the field guide. So with that, I will turn it over to Mena and the team to talk us through the development of these tools.
Thanks, Eric. So before I go on, I want to grab your attention that when we talk about managing dynamic harmful algal bloom management, it's important to recognize that this process is it's not a static one. It's not a one-time process, but it's a continuous and an evolving cycle. And at the core of that cycle, we recognize that risk assessment is a very important part, but it's not a one and done task. So it has to be updated regularly based on the new things that you're seeing at your plant, something like changes in the frequency of the bloom from one season to the other, or changes in the source water conditions, for example, that can change due to climate change, or maybe the nutrients loading in your water, or even if you have any updates on your treatment plan. So all of these things need to be taken into consideration when you're doing risk assessment. And the output of that risk assessment is kind of which risk level that your utility is at, and that's going to inform directly which monitoring tool that you should be using, and the frequency of these monitoring tools that needs to be applied, and also where you should be applying your monitoring, whether it's just at the finished water or maybe also to be included in the source water. And of course, that output of these monitoring tools, so the results from the monitoring goes back into the risk assessment in order to make sure that it's updated and it's reflective of your actual conditions at the plant at all the time. And the output of the monitoring is also the input to your response plan, because that's how you are basing your actions on, based on the things that you're seeing at your source water or your finished water. And the actions that your response plan, these things also have to make sure that you're including in these to update your risk assessment after each and every event that you're having, to make sure that your response plan is considering the actual risk that your utility is facing each year, and being updated based on actual evidence and actual data that you're collecting from your plant, and not just general guidelines. So as I said, risk assessment lies more or less in the heart of that process. So that's why I'll be focusing on the risk assessment in this part, and I'll be talking about how to quantify the risk at your plant, and then how to turn that quantification into a qualitative risk assessment in order to inform on the actions that you need to do in your response plan and the selection of your monitoring tools as well. So let's start with the risk analysis. How can we do risk analysis? And so for the risk analysis, you're going to end up with being in one of the three levels, whether it's low, moderate, or high risk level. And how you're going to end up with these levels is that you need to do a risk on many different categories. So we classify three main categories that you need to consider when you're doing a risk. That is based on your current and historical data. The first one of these categories is, of course, the risk of the presence of cyanobacteria and cyanotoxins in your source water. And I'm sure you recognize that this is the most commonly found risk factor in the already existing risk frameworks that are available before this WRF project. The new thing that we've added here is mainly also another category of risk, which is the risk of the release of the toxins in your source water. So for example, if you are a utility that you are applying a control method like an algaecide, or maybe you're having a sonication device out in the source water, how would that impact the risk of the release of toxins? But the other part as well, which is very important, very essential when it comes to HAB management, is your treatment train. How efficient, and if that treatment train is sufficient to actually get rid of the cyanotoxin in your treatment plant. So combining all three categories of the risk is going to end up with a value for the total risk of the plant, and that range of the risk of the total risk is going to correspond to a certain risk level. So again, low, moderate, and high. Each of these levels is going to correspond to a certain actions that you need to take in your response plan, and we're going to talk about these in details later in task 3. And also it's going to inform you which tier of monitoring that is required, and that tiered monitoring approach was already presented in WRF 4912, a project that was released in 2021. But each risk level corresponds to a certain tier of monitoring that it is required for that risk level. And again, Sashira is going to talk more in detail about that tiered monitoring approach. So now let's dissect these risks individually and talk about each category individually and how we can actually quantify the risk for each category. So let's start with the source water risk. So the source water risk is going to be determined using historical data for cyanobacteria and cyanotoxin. And for that, we are defining 3 main parameters to consider. First is the bloom frequency, and second is the maximum cell concentration that have been detected in your plant, and third is the maximum toxin concentration that have been detected in your plant. So we need to review all 3 parameters in order to have a comprehensive analysis of the risk of your source water. But what if your plant is at the beginning of the HAB management journey and you don't actually have data that about cyanobacteria and cyanotoxin? How can you approach this, and how can you assess the risk of the source water? So we have proposed that you use water quality data, specifically the trophic state indicators. These can help you do the assessment of the risk in the source water. We do acknowledge that this, of course, is less reliable than having historical cyanobacteria and cyanotoxin data, but it is still valuable in order to have a preliminary assessment of the risk in the source water. Some of these indicators are the phosphorus, the temperature, sea depth, and of course the thermal stratification. So now that we have 2 different scenarios for water utilities, each with different input, now let's see how can we actually assess the risk based on each different scenario. Let's start with utilities that do have historical data on cyanobacteria and cyanotoxin. This table is what you would find in the WRF guide. And on the left side, you'll see that the risk level is quantifiable into 0, 1, and 2. And these kind of corresponds to different thresholds that were obtained from the WHO guideline. And you can see the 3 parameters that we mentioned earlier: the bloom frequency, the cell concentration, and the cyanotoxin concentration. It's important to note, though, that for the cell concentration, we have 3 different ways to represent cell concentration. So first, we have bivolume, we have chlorophyll, and we have phycocyanin. And these 3 ways can be used as alternatives. So, but they are ranked, though. So we know that bivolume is the most reliable way to express how much cyanotoxin that you can have, followed by phycocyanin, and then followed by chlorophyll. So in case a utility does have bivolume data, so they can use that column just for bivolume, but if they don't, then they can use the columns for phycocyanin. And again, if they don't have either, they will have to use chlorophyll data. And so let's see, so here, so for example, if a utility has a bloom once every a few years, then they would be in a category of risk level 0. And if they do have multiple blooms in one season, they can be in the frequent risk level for that parameter. And then you will see that for each parameter, we have thresholds that have been compiled using different resources. Of course, the table here is mostly from the WHO guideline. However, in Appendix B in the guide, we have compiled a lot of other thresholds that are coming from so many different resources, such as the EPA or the Australian guide as well. So you can refer to these in case you want something that is more specific to your situation. And also it's important to note that these values here correspond mainly towards microcystis and microcystin LR. So if you have a different species of concern, or if you have different toxin of concern, then you might want to again revisit the Appendix B, which shows different thresholds for different species and different toxins as well. Now let's move to the other scenario where a utility doesn't actually have any historical data and they have to rely on the eutrophic state indicators. So again, on the left side, you will see that the risk level goes from 0, 1, and 2. And then we have 4 parameters: the CK depth, the total phosphorus temperature, and thermostratification. For this table, most of the data are coming from the Australian guide because the WHO did not have thresholds for these parameters. And because these are less reliable than the actual cyanobacteria and cyanotoxin data, we do strongly encourage the utilities that use these parameters to include at least 3 in their assessment, so that it's not really biased towards only one parameter. So at least use 3 out of these 4 parameters when you are performing the assessment using this table. Now that we've seen the table, well, how can we actually use them? Well, the guide also provides example of how we can use these tables, and I will go through one of the examples here. And this example is going to go with us throughout the presentation as well. So you might want to remember how it goes from this. So here we have a utility X, and that utility experiences or reports a frequent cyanobacteria blooms in the summer, and they have a maximum cell count of around 50,000 cells per milliliters, but they have never detected cyanotoxin in the plant before. So what they would do is they lay out the parameter and they lay out the reported value, and then using the tables that we had before, they can find out the risk level corresponding to each of these levels. So again, the frequent bloom corresponds to a risk level of 2, and a cell concentration of 50,000 corresponds to a level of 1. And even though the table that we showed earlier didn't really have cyano cell concentration, it showed cell by volume. The Appendix B also shows how you can transform from cell by volume into cell concentration. It shows different thresholds for the cell concentration as well. So you can have different expression of that cell concentration parameter. And for the cyanotoxin, we can see that since they have never been detected in the plant, they are at risk level of 0. So what the utility has to do is just sum all of these risks and divide by the number of parameters that they have used. Since they have used 3 parameters, so they're just going to divide 3 by 3, which gives them a 1, which is a moderate risk level. It's important to know that this is just the risk level of the source water, and we are still having 2 main categories of risk that we need to assess before we can reach our final end. So for that, the second category is the risk of the toxin release. And the rationale behind that is if you are applying any sort of bloom control strategy, you may risk the release of toxins into the source water, which might end up into your treatment plant, and you might end up having elevated levels of toxins just because of that control method. However, the level of risk associated with this strategy is, of course, dependent on the type of control method that you're using. So we are proposing 3 scenarios that covers most of the scenarios that can happen. One is that you are not applying any control method in the source water. The second is that you're applying control in the source water itself using something like an algaecide or a sonication device. Or third is that you are actually doing control in the plant in itself in the form of using a pre-oxidant. Now let's see how that translates into risk. So again, a table with risk level on the left side, but what's important to note here is the risk level starts at level 1 and not 0 as the first ones that we had. So the reason why we had risk level 1 as our initial risk is mainly because we cannot have a zero risk level. We cannot eliminate the risk completely, mainly because even if you are not applying any control method, you are still at a risk of releasing toxins due to environmental stressors at the source water. So even if you're not interfering with the bloom, environmental factors can still lead to a lysis of cells and release of toxins into the source water. So you can never eliminate 100% of that risk. However, if you are applying something like pre-oxidation on the site, you are still doing a control method. You're still lysing the cells, but there is a big chance that you are also destroying the toxins that you are releasing. However, on the other side, if you're using something off-site, such as using an algaecide or a sanitation, these methods have been proven to be quite effective in removing the cells or disrupting them. However, they are very ineffective in treatment or removal of the toxins. So they are at the risk of release of toxins in the water without a chance of removing them from the water. Now let's move into the third and the last category of the risk. So here we have the risk of ineffective or insufficient treatment, and that is going to depend mainly on your treatment train. So instead of going through treatment trains and like each treatment process, we group treatments into bigger groups. So we have something like conventional treatment, which entails coagulation, flocculation, sedimentation. We have pre-oxidation regardless of the pre-oxidant, and then we have other parameters or other processes as well. I'm going to go walk you through them, so the different scenarios that we proposed. However, as you can see in the table, we proposed pre-oxidation, and we have two different things. One is below threshold and one is above threshold. And that threshold I'm going to talk about in a bit. However, a threshold is mainly the amount of the oxidant that's required in terms of CT that is required to remove the cells and remove the released toxins as well. So if you are releasing the toxins without removing them, you are at a greater risk of insufficient or ineffective treatment. But if you are applying the same oxidant, but with a higher CT that is above that threshold, then you are at a less risk of having toxins in your plant. So other categories can include as well advanced treatment. And as we cannot go through advanced treatment one by one, we kind of left it open to the utility to assess what kind of advanced treatment that they are using, and if it's effective against cyanobacteria or not. And for that, they can use different literature resources, but we also encourage them to use experimental methods in order to assess how effectively it is when it comes to cyanobacteria and specifically cyanotoxin removal. And so we proposed a lot of scenarios that kind of encapsulates almost all the scenarios that a utility can have when it comes to the arrangement of treatment and the type of treatment that can be applied. And you can see that on the right side, you can see that if we apply oxidation after conventional treatment, we are at a less risk than compared to if we applied oxidation before conventional treatment. And that is mainly because conventional treatment can remove cells, intact cells, without risking the release of toxins in the water to a great extent. So you are reducing the risk of release of toxins in the water. So now let's talk about the threshold and how can we come up with that threshold. So the table is also in the guide, and it shows different CT thresholds for each oxidant corresponding to each toxin in interest. So we have microcystin LR, we have cylindrospermopsin, and we have anatoxin A, and we have 4 different oxidants. And in order to come up with these numbers, we use Cyanotox tool. I'm going to have a QR code at the end of the presentation that can guide you towards that tool. However, we had a lot of assumptions in order to reach to that CT value. So first, we were assuming worst case scenario when it comes to conditions. So we are talking about pH 8 and temperature 25, which is a high temperature that is corresponding to a higher risk of bloom. And then we have an assumption of what if our conventional treatment cannot remove the cells. And another assumption that we made is we are already starting with a high level of extracellular toxins, which corresponds around to 12 micrograms per liter. That is the alert level number 2 of the WHO guideline. So this is our input extracellular concentration, and our final extracellular concentration, we want it to be around level 1, alert level number 1, which corresponds to 1 micrograms per liter of microcystin LR, for example, or of any of the other toxins. And then we also assume that the toxins themselves, that the cells themselves already have toxins within them. That is, so the total toxin within the cells and the extracellular are around 10 times of that, of the alert number 2, so around 120 micrograms per liter, which is considerably high. And then we also assume that we're going to have an instantaneous release of toxins so that we can have a higher load of toxin versus the oxidant. And we do recognize that these are just assumptions that we have to make in order to propose a worst case scenario. So what we encourage the utilities to do is to actually apply their own numbers so that they can use their own conditions, and they can use their own oxidant of interest, and then they can use their own toxin of interest. They can use their own maximum cell concentration in order to come up with the CT values that are required to reach that threshold that we mentioned in that treatment train. So now that we have covered all 3 parts of the risk, how can we combine all of them in order to find that total risk level? So remember the example that we had earlier, we were talking about a utility X. So that utility X had a source water risk of 1, corresponding to 1, according to the table that we created. But that utility kind of have a pre-chlorination system with a maximum achievable CT of around 50 milligrams minute per liter. And then they have a conventional treatment with dual media filtration followed by ozonation with a CT of 1.6 milligrams minute per liter. So based on these givens, we know that the source water risk was moderate risk, which is corresponding to 1. And the risk of the release of toxins due to using a source water control, since we're using pre-chlorination, that puts us into the moderate category, which is the risk level number 1. And for the treatment train, here we can quantify that the treatment is using pre-oxidation with 50 milligrams minute per liter. And if you recall the threshold from the earlier table that I was showing, the threshold for chlorine, free chlorine with microcystin LR was around 138 milligrams minute per liter, which means that this value is below the threshold that we are proposing. And that treatment train also consists of conventional treatment followed by ozonation. However, the ozonation had a CT of 1.6, which is above the threshold that we are proposing. So overall, that utility scored a risk level of 1 when it comes to the insufficient treatment. So now that we have quantified each of the risk categories that we have, all what we have to do is accumulate them in order to get to the total risk that we have at the utility. And with that, we can see that this utility scored in a moderate risk level, and so it requires a second-tier monitoring. And now I'll move it to Sushira in order to talk more about that risk level and how it reflects into the response plan and the monitoring treatment, the monitoring tool required.
Great. Thank you so much, Mena. That was awesome. As Mena mentioned, I will be going more into our task 2, which is compilation of monitoring methods, looking at how to develop a monitoring program based on your risk levels that Mena just showed, and how we apply the tiered monitoring approach with these methods. So you will see in the final report that WRF just published that we have put together a sample monitoring program development spreadsheet based on these different risk levels. And as you can see, within each of these categories, you'll have definitions on what that means that you're in a high-risk plan. It's like the system or time of the year that blooms occur commonly and consistently. Moderate risk, which is system or time of the year where sometimes you're seeing the blooms, and low-risk plan where it's highly unlikely or moderately unlikely, but monitoring is still recommended because there's been some events in the past. And for each of these, we wanted to tie the scoring back to MENA's framework. And like you've seen in the example, a moderate risk category is between like 2 and 4. So high risk, on the other hand, would be more than 4 on your risk score, and a utility with a low risk category would be usually scoring less than 2. In addition to these, you'll also see some guidance on sampling frequencies and sampling locations that the utility needs to be focusing on under each of these risk plans. And finally, what kind of monitoring methods you need to pick to measure the water quality indicators, cyanobacteria and cyanotoxins in source water, in plant, and finished water matrices. So before we jump into the methods, I wanted to show some key parameters that we looked at while including these method cards and developing the field guide, which is very important for utilities, as most of the times, depending on which risk level you are, you're always looking at costs. How much does it cost to develop these methods in-house versus sending these samples outside? Reliability of the methods, how reliable the method is in giving you consistent data that you can use for interpretation and taking response plans based on that data, and also the third one being complexity, how complex it is to troubleshoot when something goes wrong, like an LCM SMS instrument, as some of you might already be working on it, and you know that it's a really complex system, and when something breaks down, you either need to have a service agreement with the vendor, or you need to have somebody in your lab who knows how to troubleshoot that system. So it's something that we kept in mind as we put these method cards together to show the reader where each of these method cards rank on these parameters. So that brings us to the field guide. The field guide, as WRF has envisioned, should be a compendium of commercially available screening and monitoring tools that are available for field application. And the field guide is supposed to help people at utilities, including water treatment specialists, water quality teams, and operators, to understand which monitoring methods they need to pick based on the risk levels, based on analytes of interest, the water matrix, and the 3 factors that I just talked about, like cost, complexity, reliability, and also compliance needs. Based on which region you're in, you might have different compliance needs based on the regulatory requirements in your region. So for compilation of this field guide, we looked at 3 categories: water quality indicators, cyanobacteria, and cyanotoxins. We looked at different WRF projects. As Eric mentioned early on, we wanted to build on existing WRF guidance. So we looked at 4912, 4914, 4692. We looked at guidance manuals produced within the US, within EPA and Ohio EPA, and WHO, World Health Organization guidance manuals, and of course, literature as and when we needed to dig in a little further about methods that are not standardized yet, but are still commercially available. So to give you a peek into the field guide, this is what it will look like as soon as you open it. You'll see the table of contents, and I wanted to show you a quick peek on how many methods are under each of these categories that I just mentioned: indicators, cyanobacteria, and cyanotoxins. I'll walk you through some example method cards, and then we will hand it over to Hussein to talk about how data from each of these methods needs to be managed and interpreted at the back end. So the first example I wanted to show is remote sensing, an emerging and exciting technique, a relatively inexpensive technique compared to other routine screening tools. It focuses on water quality indicator measurement. It has optical sensors. Basically, you can use satellite imagery, optical sensors that are mounted on satellites, or if you're really, really interested in drones, you can place these optical sensors on drones and have a dedicated system for your water body. Basically, these sensors measure sunlight being reflected from the water body based on differential absorption and scattering of light, depending on the particulate and dissolved matter present in the water body. It can measure, the technique can look at various parameters like turbidity, chlorophyll A, phycocyanin, color, and cell density in some cases. And you can see that we have a lot of information on the card, so I'll walk you through each of these components real quick. The first thing being the graphical illustration of the method itself on one side of the card. Huge kudos to Hazen Graphics team on this. They did an amazing job on making them visually really appealing. And so that gives you an overall visualization of the method and what kind of data that it's generating, what kind of graphs that you'll be seeing. And then we have the overview, which is a short summary of the method. This is for utility personnel flipping through the cards to understand at a high level what the technique does and what the level of effort can be anticipated from this. And you can also, you probably can't see, but there's a small turnaround time tab on the right-hand top corner. So that tells you what the turnaround time is for each technique. And then we have quick stats on the right-hand side on the bottom to show what analyte the method focuses on and what are the units, and of course, reliability, cost, and complexity. How do they scale for each of these? And finally, we have pros and cons for each method. We discuss some nitty-gritty things that that we might miss in the overview, like that we want to note, like, hey, this method is good for this, but you might have these interferences and things like that, just for the reader to know some information compared to the other methods. So that's one example, and I want to show another example on chlorophyll A and phycocyanin measurements using buoys or probes. This is another method card that falls under the cyanobacteria category, because this is an indirect way to measure your cyanobacterial biomass. But we also talk about kind of these nuances in the overview between chlorophyll A and phycocyanin. This field guide being specifically focused on cyanobacteria, we want to note that, hey, phycocyanin is specific to cyanobacteria, but chlorophyll A, you can find it in green algae and other phytoplankton, not necessarily cyanobacteria. So there is a stronger correlation with one parameter than the other. So same thing, it talks about the overview and those kind of nuances and pros and cons and things like that. Finally, I wanted to show one of my favorite cards. It's the enumeration with flow imaging microscopy. As some of you might have known, flow imaging microscopy is a semi-automated enumeration technique that some utility would consider if they are in a moderate risk category and if they have frequent need for enumerating biomass and they want to establish a baseline, do monthly monitoring during non-bloom months, and do weekly monitoring or daily monitoring during bloom months. And it's a lot of effort for an analyst to do manual enumerations for that kind of frequency. So that's where flow cams can be very helpful and speed up the turnaround times. You can set up basically up. So for those of you who are not familiar, FlowCam it basically operates based on a water sample being flown through a flow cell, and there's a camera that captures images of the water sample that's passing through, and it can detect the particles based on the size, based on morphology. And you have reference libraries that comes with the FlowCam, but sometimes you might have to tweak the reference libraries, make your own reference libraries. So the image detection system built in basically looks at the sample images and the reference libraries, matches it up, and gives you an enumeration. And you still have to go back, do some cleanup and quality control and everything, and make sure it's not picking up the wrong images and classifying that as microcystis or something. But overall, it's been a great method, and we've heard a lot of successful case studies on this method at different utilities. So that's my third example. And with that, you can see as you flip through the field guide that we have covered methods that are ranging all the way from low reliability to high reliability. And needless to say, with that increase in reliability, the cost also goes up. And what we've seen with different case studies and something we're recommending in the field guide is to pick multiple methods on this spectrum, whichever monitoring plan you're in. Obviously, as your risk level goes up, you will have to do higher reliable methods for compliance purposes or for your own monitoring purposes. But even if you're at a moderate or low risk level, we recommend typically using more than one method. Pick a low reliability method for regular screening, and then have your moderate or high reliability methods for confirmation and triggered monitoring. Because we've seen when you use more than one method, it's easy to look at data discrepancies, but I will pass it on to Hussein to talk about the other side of the data discrepancies. But typically, we've seen that it's been successful when utilities are using multiple methods to kind of cross-check each method as you're monitoring, and as your risk level goes up, it becomes even more important to do that. So you've seen what kind of tiered monitoring plans that we are presenting in the project based on the risk levels. You've seen how to pick the methods and what kind of method cards that are available for you to look at. And now I will pass it on to Hussein to talk about what happens when you use these multiple methods for monitoring and how to manage the data on the back end. So over to you, Hussein.
Great, thank you, Sushira. So now coming into sort of one of the final elements of this field guide will be on performing the actual data interpretation. So here to start, I'd just like to highlight something initially, which is that the baseline risk assessment which Mena presented will only provide a starting point for where a utility should be placed. So low, moderate, or high risk. But that's by no means the end of the story for that given utility. We recognize that a utility's risk profile can change over time, and be that due to seasonal variation, nutrient inputs, climate change, or changes like implementation of source control where it was not there previously. And that will cause the utility's risk profile to change from low to moderate to high risk. And we've included some of the triggers for how to go between these categories. So I won't go over what low risk entails or what the tools are there that can be selected. But I'll just highlight that if you are placed in a low risk monitoring category, then we have instructions to switch to a moderate risk plan when the biological activity that's being monitored by these low cost first tier monitoring tools exceeds some baseline based on your historical data. And there's a little bit more information in the guide about how exactly to do that. And similarly, for a moderate risk plan for utilities that do typically experience cyanobacterial blooms, where their monitoring may be more regular, they may want to switch to a high risk plan and accelerate the type and frequency of monitoring that they do if the cyanobacteria exceed certain thresholds, or they may be reduced to a low risk plan if they see no cells or no toxins in consecutive samples, or if they're in a place that has strong seasonality, that the algal season has ended, and then you can switch back to a low risk monitoring plan. And finally, for high risk, this would be much more aggressive sample collection with more expensive but more reliable tools to get more detailed information. But if time after time the samples are coming back consecutively negative or non-detect and the bloom season has ended, then it may be acceptable to switch down into a more moderate risk plan. Now that we've selected a tool and we know our risk level and the types of tools that we should be picking from, how should we interpret the data that is now being generated? So if we've got an algae probe that generates chlorophyll and phycocyanin data, here we provide some of the different types of data analysis tools that have been reported for that type of data. And we do that for basically everything that we could find in the literature, and also provide resources that you can directly rely on in the guide itself. So coming to a more specific example, if we imagine utility X, coming back to Mena's example in the initial risk assessment, where we required a moderate risk, which requires a second tier monitoring tool. The personnel at that facility browsed the method cards and they decided on purchasing an algae probe based on the various factors. Then they start collecting data on phycocyanin, chlorophyll A, and water quality. And they decide that they would like to create a model that will estimate cyanobacteria biovolume based on the data collected by the algae probe. And to do that, they decide, okay, so we'll collect samples every week and send it to a lab to measure biovolume and see if we can relate that biovolume measurement in the lab to the online or real-time data that we get from the probe. In the guide, you'll find resources on how to do this. And this is just one example. There are many different examples based on different tools and different types of data that are shown there. This will show you, for example, how exactly to set up your Excel file that contains this data. So with the columns, the column headers, and how to put in the numbers, as well as the tool that can be used to interpret that data. So in this example, we'll be using RStudio, which is free, publicly available statistical analysis software. We provide the code as well. It's ready to go. The only thing that you need to do as a user, if you wish to apply this method, is change these two lines shown here, where it has the directory path that leads into your file and what the file name is. So as long as you've formatted the file in the way shown on the previous slide, you can plug it right into the code. This code is right there in the guide itself, and you can hit run, and it will generate plots that maybe look something like this. So you'll get a nonlinear regression between, in this example, there are many others, biovolume versus phycocyanin and biovolume versus chlorophyll A. And then you see that there is this equation that's generated at the top of the screen. And you could use that equation to calculate site-specific thresholds for your own facility based on your own data, if you wanted to interpret the data in that way. So these resources are available for you. Another important aspect of this project that I'd like to highlight now is addressing discordant data. So we would recommend, I think most people would, that it's good practice to incorporate more than just one monitoring tool. And that's especially true for moderate and high risk utilities, but that sometimes the use of multiple tools can result in apparent contradictions. And here we try to address what are the possible causes of these apparent contradictions and what are the suggested actions. So let's have a look at a couple of quick examples. The first one, if we're monitoring for cyanobacteria cells, and we've got two methods. We have an observation by microscopy where no cyanobacteria cells are present in the sample that was sent to the lab, versus we have, let's say, a phycocyanin algae probe, which says that there is a positive measurement of phycocyanin greater than the baseline in our sample, which would indicate that cyanobacteria cells are present. So how do we reconcile this apparent contradiction? Well, some possible explanations could be that the phycocyanin probe is picking up remnant extracellular phycocyanin following cell death. So the cells have died, they've lysed and degraded, and they're not present anymore. So the microscope doesn't see them, but the phycocyanin remains for a short time after cell death. That could be one. Or it could be that truly no cells are present, but that phycocyanin is experiencing interference in the sensor due to the presence of other things in the water. Or it could be that the microscopy and phycocyanin samples were taken at different times, and so they're not really measuring the same thing. So in this case, suggested actions, if we had this result, might be to collect a sample for microscopy again, if those samples were collected more than a day apart. Or if they were collected at the same time, then probably investigate the potential for interference due to chlorophyll or turbidity on that phycocyanin reading. So fairly straightforward in terms of how we would approach this. In another example where we're now quantifying cyanotoxin concentrations, let's look at this scenario. We do an ELISA test, which comes back positive for total microcystins. But we also had a sample that was sent to a lab that analyzed for using LCMS for microcystin LR, and that came back negative. So our first reaction would be, okay, it's possible that microcystins other than LR are present, and that's why it was positive in the ELISA for total microcystins, but negative for LR itself. What if we also had qPCR measurements on the same sample, and these ones came back negative for the MCY gene, which is the gene that's responsible for the production of microcystins? What would the explanation be there? Well, it could be that there are no microcystin-producing cells present in that sample, but that extracellular non-LR toxins are remaining in the water. And so we see that these explanations will reconcile these differences. And we have some suggested actions where, in this example, they will differ based on the guidance provided by the local water authorities. And I'll give an example of this on the next slide, but I'd just like to highlight that this shows the value in having more than one monitoring tool, where if we were to rely solely on, let's say, qPCR, and it comes back negative, the toxin genes are not present, well, it misses the possibility that the toxins are present, but due to in their extracellular form and not being bound to cells. So having more than one monitoring tool will allow these different scenarios to be elucidated and discovered. So here's an example of what happens when we consider different considerations in local jurisdictions. This is an example of, so coming back to the previous one, if we had an ELISA result that was positive, but an LCMS result that was negative for microcystin LR. If we're in Ohio, USA, we see that our standard that we're working towards is 1.6 micrograms per liter of total microcystins, or 0.3 micrograms per liter for a certain subset of the population, and that's determined using ELISA. In contrast, here on the other side of Lake Erie in Ontario, Canada, the standard in drinking water is 1.5 micrograms per liter of microcystin LR, and that must be determined using LCMS. So the suggested action would differ depending on whether you're in Ohio or in Ontario because of these local considerations. So in Ohio, you would accept those ELISA results and potentially resample for confirmation. In Ontario, you would accept the LCMS results and you would not be required to resample because the standard is based on LR and you don't have LR, so that's the end of the story. So keep that in mind when interpreting some of the suggestions that we placed together inside of this guide. And now I will turn it over to Eric, who will provide a summary of the project, and then after that, we'll be taking on some questions from the audience.
Thank you, Hussein, and thank you to Mena and Sushira as well for the really riveting walk through the guidance document and the summary of the materials that are in there and the examples. I think the examples are probably the most useful part of this entire guide, just understanding how you can utilize these materials and get yourself out of situations of potential misunderstanding. So to summarize the project, the goals, these project accomplishments are tied directly to the project goals. We were successful in developing a risk assessment framework for utilities, considering risks from source water vulnerability, toxin release, and insufficient toxin treatment. We compiled and synthesized available methods, commercially available, and for the field guide. We were successful in developing guidance for data interpretation, resolution of the discordances and interferences, as Hussein just described. And the utility field guide is available on the Foundation website as a public plus resource. So it's readily available and filled with these easy to use method cards that have all sorts of information. And then finally, perhaps very importantly, the resources are designed to be utilized in conjunction with all sorts of additional resources that have been developed through the Water Research Foundation and through AWWA. Some subset of them here shown on the right with QR codes that you can go ahead and link to many of these available resources. If I'm not mistaken, all of the Foundation resources are available public plus, so you just have to register with the website and you can have access to them. And then the AWWA Cyanotox tool is available to members of AWWA. And it's been a real pleasure to be involved in all of these projects and to have this team, some of which are here today that worked on all of these projects, really. It's been a great group that's gotten together to address many of these cyanotoxin-related projects for the Foundation. And with that, I just wanted to acknowledge the folks involved in this particular project. Of course, Sydney was our project manager from the Foundation. At Hazen, in addition to Sushira and myself, Chris Owen, Liz Crafton, and Josh Weiss were also very instrumental. University of Toronto, of course, we saw Mena and Hussein today, but Professor Ron Hoffman also did quite a bit of work on this project as well. And additional co-PIs, Eric Wirt from Southern Nevada Water Authority and Arash Samiade from Australia. We had lots of partner utilities and it's just been a real joy to be able to work on this project and the other cyanotoxin projects with the great team that's been assembled to develop these projects. So with that, I believe we're ready to take Q&A.
Thanks, team. We only have a few minutes left, so we're going to jump right in. And my first two questions are actually going to go to Mena because they relate to the risk framework she described. So the first question is, would you consider using satellite data to fold into the source water risk tool?
For sure, yeah. So remote sensing or satellite data can be used as like the, historical data for cyanobacteria. So that can be for the parameters of the cell concentration part. Depends on which data they were using. Sometimes it's chlorophyll from the satellite data. So it can be used instead of one of the parameters that we're using, but we still have to use something like bloom frequency and maybe cyanotoxin as well in conjunction with that.
Okay, the next one is on the risk of ineffective treatment. And so did you consider nanobubble oxidation in particular, or sorry, ozonation in particular?
So for ozonation, regular ozonation, we do consider it as part of the oxidation. So you can find it in the table for the thresholds that we've developed. For any treatment processes that are considered advanced treatment processes, you really have to quantify how effective they are in terms of cyanotoxin removal. So it's going to be case by case. That's why we grouped them into just one group of like advanced treatment. We didn't classify into each or how each process is going to or how well it's going to treat cyanotoxin. So it's going to be on the treatment utility to decide if that is suitable for treatment of cyanotoxin or not.
Thanks. We'll send this next one to Eric. This work seems like it's developing the foundation for water safety plans for utilities to manage HABs. Have you thought about integrating this work into a WSP approach, which would bring it all together into a whole program?
We have, and really appreciate the comment. Yeah, we absolutely have thought about engaging this approach in these broader WSP type projects. I don't know how else to answer that other than we're working on that approach. Great thought.
I'm not sure who wants this next one, so I'll throw it out there and then have you all tell me. Is there any escalation considerations for the impacts of climate change? For example, characteristics of the water body, or sediments and potential desorption risk of nutrients?
Yeah, I can probably answer that one. I would say that yes. So it's, I would say, inherent into the way that the risk assessment is done. So we don't recommend performing the risk assessment only once. If there is escalation due to climate change and a real change in the behavior with respect to cyanobacterial blooms in that water body, then that should be captured in a subsequent risk assessment. So as well as anything else like sediment deposition, nutrient addition, things like this.
Okay, and we've got time for one last question, and it's on the risk side as well. So the question is, we understand that cell density doesn't necessarily correlate to cyanotoxin production and might depend on other stressors. Does the risk assessment breakdown or your tool reconcile this complexity?
That's a great question. You're right in that there is no way to correlate the presence of cells or their concentration to cyanotoxin concentration. So that's not what we are attempting to do here. Instead, we're trying to use these monitoring tools to provide us with thresholds or indicators or alarms to let us know when we should be collecting a sample to investigate the potential presence of cyanotoxins. So a lot of the thresholds, for example, the one by the World Health Organization is based on a conservative estimate where you've got a certain number of cells. And now imagine if all of those cells were toxin producing and if they were all producing toxins at the same time, then you could reach a concentration that could be of concern. So it's this type of conservative thinking that allows us to trigger when a sample should be collected for toxin quantification.
Okay, that makes a lot of sense. And so with that, I want to thank Eric, Hussein, Sushira, and Mena. You're fantastic speakers. These are really great reports. All of the reports are now available on WRF's website. I want to thank the audience for sticking with us through the end. Please stick around just a little bit longer to fill out a survey at the end so we can find out what you thought about today, but also what topics you're interested in learning more about in the future. A recording of today's webcast and the slides will be available on the website after today. And with that, I just want to say thank you all. I hope you have a great rest of your day.
Thank you, Sydney. Thanks.